Basically, we played that game because our next unit is probability. And this should be our last, at the very least, big unit. All right, we may have like a extra lesson or two before the end of the semester, but nothing that will be majorly tested on. All right, so this unit's the last major test. Now, the reason we start with that game is because most probability is, mainly used in gambling. Like, obviously, there's a lot of ways you can do probability, but when people think of probability, they think casinos, Las Vegas, things like that. And casinos are experts in probability, all right? Because, think about it for a second. What is probably the most popular dice game in a casino? Say again? Blackjack's a card game.
That's roulette.
That's roulette. I'm thinking craps. It's a dice game where you throw it, and typically you want to land on a 7. All right? Another name for it's lucky sevens. Now, why do you think they picked 7?
It's the most common chance.
It is the most common chance. All right, so a 7 is the most common number. Now, as you guys saw with the numbers that we picked, the quickest rounds were 6 and 5. All right, 11, 12, and 2 were the hardest because there was only one outcome for each one. All right, so it was pretty hard to get those numbers. Now, so today we're just going to talk about the bare minimum basics of probability, which you should have learned back in middle school. All right, so this is just stuff that you probably already know about probability. There's nothing like new here today. So, just some basic terminology of probability. An experiment is some process that occurs with well-defined outcomes. So, for example, if we turned our games into an experiment, basically how many trials we would have until we hit this number, that could have been an experiment. All right? Outcome is the result from a single trial of the experiment. Equal likely outcomes are when the outcomes of an experiment all have the same chance of occurring. So, here's my question. When we were doing the dice game, was all numbers 2 through 12 equal likely to happen? No. Because there was only so many ways you can get some numbers. 7 being the one with the most ways, but 2, 11, and 10 and 12. No, not 10. 11, 12, and 2, there was only one way to get it. 3, 2. All right. Now, yes. Now, shh. Now, what about if I took away one of the dice? All right, so I only had one die, and we played death number with one die, meaning I only could get a 1 to a 6. Is that equal likely of happening? Yeah. All right. An event is a collection or set of one or more outcomes. So each round was an event for us. And then the sample space is a collection of the set of outcomes of an experiment. So the list of numbers we ended up getting for each round, that was the sample space. All right, so let's just do some very basic probabilities. So an experiment is run where by a spinner is spun once around a circle with 5 equal sectors that have been marked off as shown. So for this situation, what's the experiment? Spinning the spinner. So the experiment is just spinning the spinner. All right. What could be one outcome? Someone hasn't talked yet. 1. What's another? 5, 2, what else? 4 or 3. So any of those individually could be outcomes. Okay, what is the probability of spinning the spinner and landing on an odd number? 3 out of 5. So you have a 3 out of 5 chance of landing on an odd number. Because there's 5 overall. There's only 3 odd numbers, being 5, 1, and 3. Now, what is the event here? So what's the main outcome we want? Odd numbers. So this right here is the event. Now, what are the possible outcomes? The possible outcomes of the event. 1, 3, and 5. Pretty straightforward, right? This should be a review for you guys. Now, Will, can you shut the door for me, please? Now, this helps us define the basic formula that takes many probability calculations. So the probability of an event E, so you'll see that as big P of E, is given by the ratio N of E over N of S, where N of E is the number of equally likely outcomes that fall into event E, and N of S is the equally likely outcomes that fall into the sample space. So remember, an event is what we want to happen. The sample space is what could happen. All right. So for example, with the die, all right, let's say I wanted just one die. If I was rolling one die, I wanted an even number. That's the event. The even number that I want is the event. The sample space would be 1 through 6. So every number on that die, because that's the possibility that I have. So given the above definition, between what two numbers must all probabilities lie? So any probability between what two numbers does a probability always have to lie between? 0 and 1. Why 0 and 1? Right, because we're talking about fractions. Typically, you'll see probabilities in percentages, and percentages can't go past what? 100, which is 1 as a number. All right. So again, this is mainly because we're dealing with true fractions. You can also think about it as a percent. And we can't go past 100%. Now, typically when we're doing probabilities, unless we actually do an experiment like we did with our game, we're dealing with theoretical probability. So theoretical probability is just we don't have to run the experiment to determine the probability of an event. We simply must know the number of equally likely outcomes in the sample space and the number of those outcomes that fall into our event. All right. And typically these are with things that most people generally know what the outcomes will be, possible outcomes. All right. So a fair coin is flipped 3 times, and the result is noted each time. The sample space consists of the ordered triples, such as heads, heads, tails, which would represent a head on the first toss, head on the second toss, and a tail on the third toss. They first want us to draw a tree diagram to show the different equal likely outcomes in the sample space. So remember, a tree diagram just kind of maps out everything that's going on. So you can either do this starting at the side or you can start at the top and work your way down. It doesn't matter. I'm going to do to the side. So how many outcomes for the first toss is possible? So if we toss a coin, how many outcomes are possible? 2. And what are those 2 outcomes? Heads, tails. So let's say that was my first toss. Now, let's say I got heads for my first toss. Second toss, what are the possibilities? Heads or tails? What about if I toss tails the first time? Heads or tails? And then here, heads, tails, heads, tails, heads, tails, and heads, tails. All right, so these are all different combinations of the different tosses that we could have. Now, we're going to take all of these and list them out. All right, it's ordered triples. So we're just going to start at the top and work our way down. So we first have heads, 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 tails, heads, tail, heads, heads, tail, tail. So we've gone through all the heads probabilities. If that heads was our first toss. Then we have tails, head, head, tails, head, tails, 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 head, tails, tails, tails. So how many outcomes did I have total? 8. So we had 8 outcomes total. But remember, in this case, order does matter. All right. So sometimes order doesn't matter, but we actually want to know what's the probability that heads will be our first toss, tails will be our second toss, and heads will be our third toss. All I'm doing is just pulling from the table. So like, here's my first, second, third, fourth. So that's all my heads. And then for tails, here, 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 and here. So basically, I'm just picking a branch and then I'm just following it. All right. Now, based off of what we listed here, what's the probability that I will get all heads? 1 out of 8. So there's 8 possible outcomes, but there's only 1 where I get all 3 as heads. How many outcomes are there that'll give me exactly 2 heads? 3. So 1, 2, 3. So 3 out of 8. Now, last one. the probability that I get all heads or all tails.
1 out of 4.
1 out of 4. So what does or mean? Does anyone remember what or means in terms of probability? So there are two words in probability that you see pop up a lot, and or. What's the difference? Well, and how to find it, yes. But what do they actually mean? Does anyone know? Right. So or means at least one of those outcomes has to happen, and means both has to happen. So or means at least one of these outcomes has to happen. And remember, you can typically see that using the union symbol. So we want either all heads to happen or all tails to happen. There's 2 out of 8 of a chance. Simplify it down, 1/4 of a chance. All right. Or means at least one, whereas and means both. So, is it possible to have all heads and all tails? No, it's impossible to have all 3 tosses to be heads or all 3 tosses to be tails. So, if they asked us for and, the probability would be 0. All right. Now, sometimes we must quantify chance by observing observations that have been made in the real world. In this case, we talk about empirical probability. All right, so in other words, we did a test or an experiment, we got some data. The empirical probability is what we pull from that data. All right. So, a survey was done by a marketing company to determine which of 3 sodas were preferred by people in a blind test. And the results were shown. So, if we look at this table here, here's the different soda types, A, B, and C. Here's the number of people who preferred. And then what's kind of my most important row here? The total. Because more likely than not, a lot of my probability is going to come from that. So the first one, find the empirical probability that a person selected at random from this group would prefer soda B. So first off, how many people were there total? 53. So that should be your denominator. And how many people preferred 53? 24. So 24 out of 53 people preferred soda B. All right, so that's the chance that we're hoping to get every time. Now, what would that be approximately? So the 2 decimal places. 0. What? Do 24 divided by 3, round to 2 decimal places, so to the nearest hundredth. 0.45. Now, why did they say that 2 decimal places is the standard? We can change it to a whole number percentage. So just for funsies, if I change this to a percentage, what would it be? 45%. So there's about a 45% chance that people will prefer soda B. Now, find the empirical probability that a person selected at random from this group will not prefer soda A. So we don't want them to like soda A. So we're still doing this out of 53. How many people did not like soda A? How do you know? You add B and C together. So we do 24 plus 11. So this would be 35 out of 53. So that's approximately what? 2 decimal places. 0.66. So that's approximately 66%. All right, now we're not quite done with notes. So go to page 5. All right. Last thing we're going to do is talk about Venn diagrams. So remember, Venn diagrams, good way to show different outcomes and organize different outcomes. All right. So if you have a 3-circle Venn diagram, all right, how do you typically read it? So where is all 3 being liked? The dead middle, so right here. Then these intersections of 2 circles means they like both, but not all 3. And then if they're just by themselves, they only like that one person. But what if they're outside the Venn diagram? Neither. But they're still in the sample space. So this Venn diagram will show a survey of faculty and graduate students at a University of Florida's film school revealed the following information. So in other words, they're asking who liked which three stooges the best. So Mo, Larry, and Curly. Now, if we're making our own Venn diagram, where should we start? In the middle. So whenever you're making a Venn diagram, always start in the middle. Why? Well, what's going to happen when we start getting to the ones that only admire one of them? Isn't there going to be some overlap? Right. All right. Because, for example, the very first sentence, 51 admire Mo. Does that mean 51 people just admire Mo? Or they just like him in general? That means they don't like any other students, they just like Mo. So, guys, in probability, they're very specific. If they say just Mo, it's truly just Mo. They're saying that 51 people total like Mo. So that can include the people that like Mo and Curly, Mo and Larry, or all 3 of them. So that's why we start in the middle, because it accounts for overlap. So you always start in the middle and work your way out. So if I'm starting dead center in the middle, which sentence am I starting with? 24 admire all 3 stooges. So in the dead middle, we're going to put 24. Now, if we're going to work our way out, now we're going to figure out how many people just like Mo and Larry, Mo and Curly, and Larry and Curly. So we're going to work our way up. So 36 admire Mo and Curly. So if 36 total like Mo and Curly, meaning that they all fall in this part of the circle, how many only like Mo and Curly? Meaning they don't like Larry. Nope. 12. Why? Right. So it's saying that 36 people total like Mo and Larry. That includes not Mo and Larry, Mo and Curly. That includes the people that also like Larry as well as Mo and Curly. All right. Because what I highlighted right here, that's where that shows all the people that like Mo and Curly. So we have to take 36 and subtract 24 from it, and that'll give us the 12. Now, 32 like Curly and Larry. So now we're dealing with this part of the Venn diagram. So how many people only like Larry and Curly? 8. You subtract 32 by 24. Now, 34 people admire Mo and Larry. So we're looking right here. So how many people only like Mo and Larry? They don't like Curly. 10. All right. Now we're going to find the ones that only like each stooge. All right. So they're saying for the next one that 60 people like Curly. So that means we're dealing with this entire circle. Anyone within that entire circle likes Curly. So how many people only like Curly? 16. So you take 60, subtract it from 12, 24, and 8. 49 people admire Larry. So we're looking at the entire Larry circle. So how many people only like Larry? 7. And then 51 people admire Mo. So we're dealing with the entirety of the Mo circle. Only 5 people only like Mo. Now, there's one piece of information that I'm missing. What am I missing? The none. So one person doesn't like any of them. So we put that one out here. Still in the sample space, which is represented by the box, just not in any of our events. So let me see. 12, 32, 42. Nope, 7's right for Larry. And then 52. 52 plus another. Yeah. All right. So, how many people were surveyed total? So, how many were surveyed total? How do you know? Why? How many? 83. How do you know that? You just add up every single number in that Venn diagram. All right. So if I add up every single number in my Venn diagram, do I get 83? Yep. So there were 83 people surveyed. And we can do that, add up every number in the Venn diagram, because remember, the Venn diagram accounts for the overlaps. So you don't add up the numbers that's in the top of the information because that doesn't account for the overlaps. The Venn diagram does. So how many admired Curly but not Larry nor Mo? So how many total admired Curly but not Larry or Mo? 16. How many admire Larry or Curly? So it means they like one or the other. So think about this way, guys. For this question, we have our Venn diagram. Mo, Larry, Curly. If I want or, meaning they like one or the other, so at least one of them, what circles am I going to be adding up? So you're adding up the entirety of those two circles. The only part that's not going to be in there is the ones that only like Mo. Yes. Because remember, or means at least one. So as long as they like one or the other, or both, it doesn't say that they cannot like Mo as well. right? We just don't want to include the ones that only like Mo. So it'll be 70. Right. So it'll be 77. Because we also have to include that one person on the outside. So in other words, we have to subtract 6 from the 83. So how many people likes exactly one of the Stooges? So again, if I'm looking at my Venn diagram, if I want to look at the exactly one, which pieces of the Venn diagram am I looking at? The outside. So here, here, and here. That's what I'm adding up. So it would be 5 plus 16 plus 7, which is 28. And how many admire exactly 2 of the Stooges? So in other words, which pieces am I looking at? Right. So I'm looking at the overlaps, just not the very middle. So that would be 30. Now, there wasn't any exactly probabilities there. We just, was taking information out of the Venn diagram to answer questions. But they could ask us, what's the probability of someone liking only curly? And we would say 16 out of 83. All right? Because they only like curly. All right. So, any questions on any of this from today? All right. So, your homework for tonight is going to be pages 3 and 4 and page 6. So 3 and 4, which covers the first part of the lesson, and page 6, which has you guys practicing more Venn diagrams. So 3, 4, and 6. And you guys got a solid 30 minutes, so you can probably knock it out before you leave class today. Yes. Do you like using my computer?
Yeah.
So I can play with it. Get back up. Thank you.